Now that we have the equivalent circuit model of the PV cell, let us now try to get an equation for this equivalent circuit model. So let me quickly draw the IV characteristics of the PV cell. So we know it is like this. This is the 0. There are two critical points on the characteristic that all should be familiar with. One is this point where it intersects the y-axis, where the VT, the terminal voltage, is 0. The terminal voltage is 0. This point is called ISC, the short circuit current. This is ISC. This is called the short circuit current. Reason is this is the value when the terminal voltage is 0. So basically, when you short circuit the terminals, the current that flows through it is ISC. Now coming back to the other point here, this is occurring when the current is 0. When the current is 0, you have the x-intercept here. So the voltage at this point is called VOC, or the open circuit voltage. So this is the open circuit voltage. This occurs when nothing is connected across the terminals of the PV panel. Then V terminal voltage, VT, is given by VOC. Okay, so now using these parameters, we can get some insight into the PV cell workings by having a equation that models this equivalent circuit. So let us now have a PV cell which has a load connected across that called RL. So this is a generic model of the PV cell along with the load RL. This is the photocurrent IP, and there is a current that flows through this diode ID. There is a current that flows through this called I shunt, and then the terminal current. So this IP is given by ID plus I shunt plus IT, which flows out of the terminals. Now ID is the diode current, and we know from semiconductor physics the diode current is given by I naught, the reverse saturation current, e to the power of the terminal voltage across the diode, which is, if I say there is a current IT flowing through this RS, VT plus IT RS is the voltage across the diode at this point, at this node point. So VT plus IT RS divided by N uppercase VT. This is the voltage equivalent of temperature minus 1 plus I shunt. I shunt is nothing but again the voltage across this node, which is VT plus IT into RS divided by R shunt will be the current I shunt plus IT. So this is the equation that models this equivalent circuit. Let us now decode this equation further. Let us express the terminal current. Let us express the terminal current in terms of all the other parameters. So IT is equal to IP minus ID, and ID is this one, reverse saturation current into e to the power of VT plus IT RS by N VT minus 1 minus VT plus IT RS divided by RS. This represents the shunt current. So this is the important equation. This is the model that gives you the terminal current in terms of all the other parameters, known parameters. A bit of decoding is necessary here. Of course, this is a well-known equation. You will get it in any semiconductor physics book. But let me decode this for you. One variable here is Vt, uppercase Vt, which is called the voltage equivalent of the temperature, and it is given by the Boltzmann constants K into T, that is the temperature in Kelvin, divided by Q, which is the electronic charge. So this is the Boltzmann constant, and this is the electronic charge. So if you take the values of the Boltzmann constant and the electronic charge, you will get T divided by approximately 11,600. You can try it out. Take the values from a physics constants book, and you should be able to calculate and arrive at this value. Another parameter A is a scaling factor here, which is 2 for silicon. So it is a material scaling factor. And then the third one, which we don't know, is I0, which is the reverse saturation current, which also comes out of the physics of the semiconductor, which is proportional to T to the power of T, again in temperature in kelvins, to the power of 1.5 e to the power of minus VGO is the voltage equivalent of the forbidden gap energy, divided by NVT. So where VGO is the voltage equivalent to the forbidden band gap, which is approximately 1.16 to 1.21 volts. Starting from the terminal current equation that we developed, which is the model of the PV cell, let us try to get some more insights, interesting insights into the PV cell operation and its characteristics. So let me quickly draw the IV characteristics. X-axis is the VT, terminal voltage, y-axis is IT, the terminal current, and the characteristics looks like this. There is one critical point here, which is called the short circuit current operating point, and there is another critical point here, which is the open circuit voltage operating point. So first let us focus on this short circuit operating point. Let me mark it in red, and there at that operating point IT is called ISC and the voltage is 0 at that point. V terminal is 0 because you are short circuited the output terminals. So applying these constraints into this equation, you see that IT is nothing but ISC, which is equal to the photon current IP minus I0 e to the power of Vt is 0, It is ISC into Rs by N times voltage equivalent to temperature minus 1 minus the shunt component of the current, which will be written as ISC Rs by R shunt because Vt is 0. Now further we can apply some more simplifying constraints, making ideality simplifications for Rs and R shunt. So let us say we put Rs is approximately equal to 0 because Rs is a very small quantity. It is a series resistance and normally a very small quantity, normally negligible. And R shunt, which is coming across the diode, the shunt resistance is a very high value. So R shunt tends towards infinity. And using these two ideality constraints into these equations, we see that when Rs is substituted with 0, then e to the power of 0 is 1, 1 minus 1 is 0. This quantity vanishes. And ISC Rs by R shunt, Rs is close to 0, R shunt is tending towards infinity. So this quantity also is approximately equal to 0. So therefore, we come with this conclusion that ISC is approximately equal to IP, the photocurrent. So this is a very important takeaway, which means that the short circuit current here is equal to the photocurrent. So which means that this point, this operating point here, or the short circuit current operating point, will change according to the amount of sunlight that is falling on the PV panel. So that is the important takeaway from this particular discussion that we had now. In a manner similar to what we did for this operating point at ISC, we shall now focus on the operating point VOC, that is the open circuit voltage operating point. So here the voltage is VOC and the current is 0. So IT is 0 and VT is the terminal voltage VOC, open circuit voltage. So let us apply this to this equation. So you see 0 is equal to photocurrent IP minus I naught e to the power of VOC. IT is 0, therefore VOC by N VT, voltage equivalent of the temperature, minus 1 minus the shunt component of the current, which is VOC by R shunt. Now if we apply the ideality constraint of Rs is equal to 0 and R shunt tending to infinity, then we see that here R shunt being much higher compared to VOC, this will tend to 0, and therefore we have VOC, which is in the exponent here. Applying logarithm, natural logarithm on both sides, you will get VOC is equal to N uppercase VT log of 1 plus IP by I naught. So we can take this log of 1 plus IP by I naught as IP by I naught, assuming that I naught is going to be very less compared to IP, because I naught is the order of 1e minus 7, 10 to the power of minus 7 and lesser. So therefore VOC is equal to NVT log of IP by I naught. In other words, VOC is proportional to log of IP, NVT being a constant. So this is the takeaway in this case, where the open circuit voltage is proportional to the natural logarithm of the photocurrent IP, whereas in the case of the other operating point, short circuit operating point, we saw that the terminal current is equal to the short circuit current, and the short circuit current is equal to the photocurrent, is proportional to the photocurrent, whereas the voltage is proportional to the logarithm, natural logarithm of the photocurrent. So this is the major difference and the major takeaway here. There are three operating points that are important in the IV characteristic of a PV curve. One is the short circuit operating point, where the current is ISC and voltage is 0 because you have short circuited the PV source. The second one is the open circuit operating point, where the PV source is open circuited, there is no current flowing through it, therefore 0 current, and the voltage across the terminals is VOC. There is a third operating point, very important, which is called the maximum power operating point. So let us consider the power at the terminals, which is given by the product of VT, the terminal voltage, and IT, the terminal current. Let us see how this power curve looks like with respect to VT. So on the x-axis we have VT, on the y-axis we will have PT as well, the power as well. So if we take this power, how does this power curve look like? So this point we know is having 0, ISC, and the power at this operating point is 0 into ISC, which is 0. The power is 0. At this operating point, we have VOC, 0 current. Therefore, the power is again 0, and the one power point is coming at this point. So it is 0 at both extreme points. At all other points we have VT and IT, which are finite, and therefore power will increase, and then it has to also finally decrease and come to 0. So there will be an inverted V or an inverted U kind of a shape, something like this, where you have one point where the power is at the maximum. This is called the peak power, PM. And this operating point, this point is called the maximum power point, or MPP. The voltage at this maximum power point is Vm. If you drop the projection onto the x-axis, you see that it is Vm. We'll name it as Vm. And you project it further onto the IV characteristic, that will be the operating point corresponding to maximum power, where voltage is Vm and the current is, let us say, name it as Im. And this operating point is Vm into Vm, Im. So this corresponds to the operating point where the power is maximum. Therefore, it is called the maximum power operating point. So this is an important operating point, because we would like the PV source to operate at this point where it can deliver the maximum power to the load.